So we're going to start kind of with a review from what we talked about last class. We're going to be applying what we know with electron configuration and then talking about the ions that are formed for these elements here. So I'm asking several different questions here. I'm asking you to give the total electrons, which would be similar to the electron configuration, the number of valence electrons, and when we talked about valence electrons, for the main group elements, it depended what row they were in. So group 1 had 1 valence electron. Group 2 had 2 valence electrons. Moving over to boron and aluminum, group 13, 3, 4, 5, 6, 7, and 8. So the numbers in blue are the numbers of valence electrons. Remembering, however, that helium here does not have 8 because it only has a 1s shell. It actually belongs over here, the 2 valence electron group. So the goal of all the main group elements is to have 8 electrons. That's what they want. Hydrogen and helium being the exception. They just want 2. Okay, so they form ions because they're trying to get more electrons or give electrons away to get that 8. So we're going to look at the total, the valence. We're also going to name the principal energy level for each of these atoms. And then last but not least, we're going to give that ion that they form. Okay, so the reason all these main group elements form ions is because they're trying to get a full octet. That's that octet rule that we talked about last class. So let's start with magnesium. So for magnesium, to get the total number of electrons, notice all of these atoms that I have up here are neutral. Right? So when they're neutral, we said for neutral, let me write that over here, that the protons equal, I'm probably spelling neutral wrong, but protons are equal to electrons for neutral atoms. Okay? So if we know the atomic number, the number of protons, that's going to be the same as the total electrons. The other way we can figure that out is with the electron configuration. And just for practice, let's just do the electron configuration for these guys. So when we do electron configuration, we always start at the 1s, where hydrogen is. Right? It's like a map going from left to right. 1s, what's the max that can fit in the s?
2.
2, and then we move to what period?
2s.
2s is next, because we're done with row 1, so then we go to row 2. 2s, 2 is the max. And then
2.
we're still in 2, but we hit
2.
3
6.
and 6, yes. So we're at neon. So then we get to 3. What do we hit first? And which one's magnesium?
2.
2, so we're done. Okay, so this is the electron configuration. These numbers, remember, these are the electrons. So for the total electrons, we're counting all of them. So total would be 12. That's also the atomic number of magnesium because it's neutral, protons equal electrons. Now for valence, different color, valence electrons are just the electrons in the outer shell. Okay? So what that means is if we're applying it to the electron configuration, it's just the highest level. So we're going to look at the highest level being what number? 1, 2, or 3?
3.
It's going to be 3. So I'm talking about the highest principal energy level. So we're looking at just the electrons in this level. So how many valence electrons does magnesium have? It's just 2. And we can also figure that out from the periodic table. It's in group 2, so it has 2 valence electrons. You don't have to draw the electron configuration. I just like to tie it together. Okay, so like you didn't have to do this at all to answer this question. You could have just said, oh, atomic number is 12, it's neutral, electrons are going to be the same. Okay, valence electrons, well, it's in group 2. Everybody in group 2 has 2 valence electrons. Okay, but I'm just showing where they are in the electron configuration. So we've answered the first 2 questions. How many total? How many valence? Notice it's different, right? Total electrons is different than valence. Valence is just the outer shell. So what is the number of the principal energy level? 3. So principal energy level, these numbers in red, it's asking what period is it in. It's in period 3, so that is going to be the principal energy level. Abbreviate it, you just said 3. Last but not least, most probable ion. So what that's saying is what charge is it going to form? So in this case, metals always form a positive, cation. Non-metals, over here, always form a negative, an anion. So it's a metal, we know it's going to be positive. So how do we figure out the charge? Valence electrons help us figure that out. It has 2 electrons. So it wants an octet, so it's either going to lose 2 or it's going to gain 6. What do you think is going to be easier?
It's gonna lose 2, so it's gonna be a positive.
It's going to lose 2. So when it loses 2, it's going to form a plus because it's losing 2 negative charges. So everybody in this group is going to form a +2 ion. So magnesium, I shouldn't write that there because then people might think, right over here. Its most probable ion is Mg +2, or 2+, you can write it either way. All right, let's do oxygen. And this time, let's not do the electron configuration. Let's try to do it without that. So what are the total electrons for oxygen? It's neutral, 8. 8, that's its atomic number, so same number of electrons. So 8, it's valence electrons, 6. So how do you know that?
Because it's under the 6th row.
It's in the 6th row. So oxygen, sulfur, everybody in that row is going to have 6. Okay, so if it has 6 valence electrons, its goal is to have 8. Right? So what do you think its charge is going to be? If it has 6 and it wants 8, is it going to gain 2 or is it going to lose 6?
It's gonna gain 2, so it's gonna be a minus.
It's going to gain 2, so it'll be a -2. Sorry, oxygen 2 minus. And then I skipped one, didn't I?
B,
Yes. What's the principal energy level?
2.
2. So we're looking now, period. Yes. So oxygen is in period 2, so the principal energy level is 2. Different color markers. So basically taking everything we learned and just saying, okay, what do we know about this atom? Let's figure out everything we can glean from the periodic table. All right. Aluminum. Total electrons.
13.
Okay, so it's number 13, neutral, protons equal electrons. Yes. Valence electrons, so now we're looking at the numbers in blue.
3.
So valence electrons, 3. Now this one's tricky sometimes because aluminum actually is a metal. It's right on that zigzag line. Okay, but it is a metal. So metals lose electrons, meaning they're going to form positive cations. So it has 3 valence electrons, so what is it going to form? What charge?
Positive 3.
Because it's going to lose those 3, and when it loses 3 negatives, it becomes positive. And last but not least, what period or principal energy level is it in? So the number's in red, it's in period 3 here. Okay, good. All right, so what we're going to look at next is isoelectronic. So that is the definition that we didn't cover last class. So I wanted to start with this because what isoelectronic means, and I'll write that definition here in a minute, is when you have 2 atoms with the same number of total electrons. Okay, so we're focusing on total. So of the ones we did, none of them are isoelectronic with each other because this guy has 12, this guy has 8, this guy has 13. So we're going to be looking at ions and neutral atoms and seeing if the pairs are isoelectronic, if their total electrons match. Okay, so there's a couple different ways to do that. All right. The way I usually approach it, because we do have ions now, so their electrons aren't going to equal their protons when we are talking about ions. Same number total electrons. So what this means is their electron configurations are going to match. Okay, so for cations, so positive ions, they are isoelectronic with the noble gas in the row above. We'll look at an example of this here in a second. So what that means is, the cations, I'm talking about the metals, group 1, group 2, aluminum. He's kind of by himself. But they all form cations. We just saw an example of that. Aluminum formed a +3. So they lose electrons. So what that means is, let's use sodium as an example. When sodium loses an electron, it becomes a +1. Because it's in group 1, it has one valence electron to lose. Okay. Well, when it loses that one electron, it now has the same electron configuration as the noble gas in the row above. So since sodium's in period 3, it's going to have the same electron configuration as the noble gas in period 2. So the noble gas in period 2 is neon. So that means neon and sodium +1 have the same total electrons. Okay, so we're going to use this to help us match up pairs. So since we talked about the cations, let's look at the anions. So the negatively charged. They're isoelectronic with the noble gas in the same row. Because, so we just did oxygen a minute ago. We said he formed a -2 charge. So that means he's gaining 2. So when he gains 2 electrons, he has 8 total electrons, just like neon does. Okay, so oxygen with a 2-, meaning he gained 2, now is happy, just like neon's happy. He's inert, he is stable. So oxygen with a 2- and neon would be isoelectronic. So notice, since both the oxygen ion and the sodium ion have the same electron configuration as neon, that means they're also isoelectronic with each other. So every one of these has, what is neon? 10 electrons total. Okay, so how I like to approach these problems is use these rules. So let's write a couple examples down and we'll work through them. So we're going to do ammonium 2-, antimony 1-. Maybe. You get it? Just did oxygen, so maybe I won't do that one. So what you might see, something like this in your homework, where they just give you the ions, or give you a pair, and they say, are these isoelectronic? So they're asking, do they have the same electron configuration? Do they have the same total number of electrons? So when I do this, I apply these rules. So my first set, they're anions. So what I'm going to do is I'm going to look at the first atom, the first anion, and I'm going to say, okay, what noble gas is it isoelectronic with? So PO, it's way down in period 6. Where is it? So radon's here. And then we have AT here, and we have PO here. Okay, so PO, when it's neutral, just has 6, but it's not neutral, -2 charge. So that means it gained 2 electrons. So now what noble gas is it isoelectronic with? Radon. Okay, so it's an anion, so it's isoelectronic with the noble gas in the same row, which is radon. Okay, antimony, right next door. He just needs 1 electron. So what noble gas is he isoelectronic with? Radon as well. So basically, if their noble gas matches, then yes, they are isoelectronic. So that's how I like to do it. I like to go, okay, what noble gas are they? Do they match? And I'll show you the long way to do it as well in a second here. The next one is going to be a little easier for us because one of them is a noble gas. So all we have to do is figure out, okay, is beryllium, is it noble gas krypton? So does it have the same electron configuration as krypton? So beryllium is where?
Row 5.
TE, right here. So when beryllium forms an ion, when it gains 2 electrons to become a -2 charge, what noble gas is it isoelectronic with? Xe, xenon. So xenon is its noble gas. Because it's an anion, it's going to be isoelectronic with the noble gas in the same row. So we're looking at the noble gas in row 5. The noble gas in row 5 is Xe. Which row is krypton in?
4.
4. So do they match?
No.
No, so they're not isoelectronic with each other. It would be no, not isoelectronic. Let's try the last one. Now we have our first cation. So we're looking at the noble gas in the row above. So potassium is in row 4. So we're not going to say that it's isoelectronic with krypton. Not the same row. We're looking at the noble gas in the row above. So what noble gas is in row 3? Argon. Okay, so this guy's argon. That's his noble gas. Chlorine, anion, we're looking at the noble gas in the same row. So chlorine's in row 3. So what noble gas is it isoelectronic with? Argon as well. So are they isoelectronic? Yes. All right, so now we're going to try a pair, and we'll look at the long way to do it. And by long way, I mean we're going to write out the electron configurations and see if they match. So, and it'll be good practice just so you can see an electron configuration of an ion. Because all we did last Wednesday was electron configurations of neutral atoms. So it'll be good to be able to see. Any suggestions for pairs, or should I just make one up? Usually ends up bad for me.
I got one lithium plus and KR, which is, what's that?
So I'm writing them this way so that we can do the electron configurations of them. All right, so let's do krypton first since he's neutral and we're used to doing neutral ones. So we're doing the electron configuration because we're trying to figure out the total number of electrons. So 1s2 is where we start, 2s2. What's after 2s2?
2p6.
2p's. We hit the p's next, 2p6, so we're at neon. Oh, this is going to be a long one.
3s2.
And we hit the 3s2. 3p6, 4s2, so we're here, 4s2 at calcium, then we hit what?
D, so it's 3.
Yes, so the D's are always one less than the period they're in, so 4s2 and then 3D. And how many, what's the max in D?
5.
Not 5, count the elements. 10. So if you're ever not sure, just count how many elements all the way across and you'll count 10 total. I didn't draw them up there because that's a lot, but 3D10 brings me to zinc. So I'm at zinc right now. Then I hit the P's. What number?
4.
4. We're back in the P's, so we go back up to 4. D's are the only ones that would go down one. And krypton is the 6th one. Okay, so this is the long way of doing it because the electrons are these guys, so we're just counting them. Since it's a neutral atom, we could have just said, okay, krypton's atomic number is 36. It's neutral, so that means its protons are going to equal its electrons, so we have total electrons of 36. Let's do the electron configuration of lithium. This time it's a +1. So does that mean it's going to have one extra electron or one less?
1 less.
One less. It lost an electron. Okay. So I'm just going to put minus an electron to remind myself when I'm writing it that I'm going to have to get rid of an electron. I'll even write -1 electron so I know exactly how many to get rid of. Okay. So let's start writing the electron configuration of this guy. So 1s, 2, and then if it was neutral, this is the electron configuration of the neutral one, right? But we said it lost 1 electron. So this 1 electron here, he lost it. So this is the electron configuration of lithium plus. Okay, so how many total electrons does lithium plus have? 2. So are they isoelectronic?
No.
No. 36 compared to 2. Which noble gas has this electron configuration? So which noble gas is lithium plus isoelectronic?
Cation. So it
Cation.
would be in the row above. So that would be helium.
Helium. Right, so helium and lithium plus would be isoelectronic. They both have the same electron configuration. Helium is 1s2. Same one. Let's try, we'll keep krypton, but I'm going to give you another ion and we'll see if it matches with krypton. Just so we can write the electron configuration of another ion, it might be nice to. No, don't want to do that one. Yeah, I'll do that one. Okay. So now, let me erase this. I'm not taking away. Arsenic, 3 minus. So is it losing, did it lose 3 electrons or gain 3? Gain 3. So that 3 minus, the negative means it gained 3 negative charges. So we're going to add 3 electrons to the neutral version of the arsenic electron configuration. So let's start. 1s2. It's going to look very similar for our start always, right? 1s2, 2s2, 2p6, 3s2, 3p6. So far so good, right? We're sticking with the same. So we're at calcium again. We hit the D's, and D's are always 1 less, so 3D, and there's 10 total. 3p3, so this is the neutral version. So this is arsenic, right? It's the 3rd one, so we're in period 4. We hit the P block, and we get 1, 2, 3. So this would be arsenic right here. The reason it makes a -3 is because it gains 3 electrons to be happy, to have the full octet. So if it gained 3, that means we need to add 3 to this number. So what should be here? Not a 3, but a
4. Oh, that
3 plus 3 is 6. Yes. So 4p6. This is the electron configuration when you add the 3 of this ion. Do they match?
Yes.
Yes. So you can look at their electron configurations and say, oh, they match. So yes, they're isoelectronic. The other way is just to count the total electrons. So a shortcut way for this, what is arsenic when it's neutral? Total electrons for arsenic when it's neutral? 33. How do you know that? You're looking at the period, it's number 33, right? If it's neutral, the protons equal the electrons. So it would have 33 total electrons if it was neutral, and we just said we would need to add 3. So if we added 3, it would be 36. So then they match. So you don't have to draw this out. You can say, okay, when it's neutral, it's 33. But it's not neutral, it needs 3 extras, so that means its total is now 36. And so is krypton. So yes, they match.
I like that one.
This way is the long way, but I wanted to show what the electron configuration of an ion is, because you might need to do that on the homework as well. So when you're doing the electron configuration, you're adding to the last part. What we talked about. Are there questions on this? Or any other questions on anything we've covered so far? Because the very last thing that we cover in this chapter is periodic trends, which I've already talked about actually a little bit, but we'll write it out in more detail. this making sense?
Mhm.
So far, anyway? Okay, so the periodic trends, the one I'm focusing on is the atomic size. We have mentioned that when we talked about the principal quantum numbers, the shells. So what you need to know about this trend is if I give you a set of elements, a set of atoms, you need to be able to tell me the order. So which one's the smallest, which one's the largest, which one's in the middle. Okay? So for atomic size decreases as you go from left to right, and it increases as you go down. Okay, so we talked about the increasing. We've done this one actually before. So increases as you go down. The reason why it increases as you go down is because of these principal quantum energy levels. These are shells, right? When we looked at an atom, so here's my nucleus, positive center, with my protons and my neutrons in it. And then the shells are the principal energy quantum numbers. So as I add more shells, because as I'm going down, I'm adding more shells. This has just one shell, this has two, this has three, this has four, so on and so forth. As I go down, I'm adding shells. So I'm making the atom, I'm physically making it bigger by adding extra shells. We said that cesium was the largest atom on the periodic table. Francium's radioactive, so that's why he's out of the game. But cesium's the largest because of that fact. It has 6 shells. Okay? So which one is the smallest? Well, to figure out the smallest, we apply the other rule, which says we are decreasing as we go from left to right. So fluorine is going to be the smallest. Okay, why? Well, first off, the reason it's decreasing from left to right is because of electronegativity. And that's actually one of the trends on the PowerPoints. And electronegativity, this is going to be a big topic in Chapter 3. So we're just introducing it now. What electronegativity is it's the atom's desire for an electron, how much it wants an electron. And so the reason fluorine wins the prize instead of neon is because neon doesn't want an electron. Neon's happy. It's a noble gas. They don't want anything. They already have 8. Fluorine, it only needs 1, and then it'll be happy, right? So fluorine is the most electronegative atom on the table as well, because it really wants that electron. It wants to complete its shell. Since it's so electronegative, since it wants the electron so much, it's the smallest atom because it's pulling those electrons really close to itself. And when it pulls those electrons in, the electrons being on this shell, it's making the atom smaller in size by pulling those electrons close. Okay? And so it wins also because it's only in period 2, it only has 2 shells. Helium can't possibly be the smallest atom on the periodic table because it already has 2 electrons. It doesn't want anymore. It's happy. So it's not pulling those electrons tight into itself. So let's do a set and apply these rules and figure out which is largest, smallest, so on and so forth. So where should we go? Smallest to largest? Yeah, let's do that. Smallest to largest. We're going to put in order. So these atoms. So out of those atoms, which one's the smallest? Well, let's look at them to begin with. So we have magnesium here. Okay. Sulfur's here, silicon, chlorine, and then lithium's up here. I don't know why I put lithium in there, I meant to put sodium. confuse ourselves. All right. So how do we figure this out? Well, first look at them, because usually when you get a problem like this, they're going to either be in the same row or they're going to be in the same column. So that'll make your life easier. In this case, they are all in the same row. They're all in the same period. They're all in period 3. So the only rule we need to apply is the left to right rule. And the left to right rule, the electronegativity, says that it's going to decrease as we go from left to right. So is the smallest atom of that block going to be sodium or chlorine? What's your choice? Chlorine's going to be the smallest because the size is decreasing as we go this way. So the smallest are going to be over here. The halogens are going to be the smallest of their row. So chlorine is going to be the smallest. So I'm going to put like a less than so we know he's tiniest. Who's next?
Sulfur.
Sulfur. Cross him out. And silicon, right? Chlorine, sulfur, and silicon. So we're just working our way. And then who? And then sodium, yes. So as long as you know the trends, this part's not really, I mean, we're not calculating anything. We're just kind of putting them in order based off the trend. Those guys, do you want to do another one?
Mm-hmm.
So, silicon again. I didn't write them on here, so I gotta go to the end of the graph too. I think so. So what trends applying? Are they in the same group or are they in the same period? In the same group, so we're looking up and down. And we'll do smallest, largest again. I believe on the homework you're like physically taking these and placing them in different groups.
But we didn't do, well, I didn't get one for the up and down, so I'm glad you did that. It was across decreasing from left to right.
Okay. So what's the smallest out of this group?
Carbon increased.
Carbon. Carbon's the smallest because he's up here. He only has 2 shells. We're going to be increasing shells from then on out. So then who's next?
Silicon.
Carbon and silicon. Germanium. Last but not least, PB or lead. So that's the last topic. They talk about electron affinity as well in the PowerPoints, but you're not going to be asked any questions on it. We're just kind of introducing that topic. So that's why I focused on atomic size. All right, so we still have 15 minutes left. So we can review another thing. Do you want to do nuclide symbols, electron configurations, orbital energy diagrams, ions, isoelectronic? Any questions from the homework or anything like that? Octet rule. We've covered quite a bit on ions and the octet rule, so you're prepared for chapter 3 already, knowing that stuff. Because that's what we're carrying it into.
Yeah.
Everything's going to be connected.
Does it have to be a question on this? Or can it be a question on lab?
Give me a question in lab, yeah?
Okay.
Maybe
It kind of
dosage lab?
Uh-huh.
Okay.
It kind of me, number 3. Lab 14.
Lab 14, yes.
Yeah, lab 14.
Oh.
Yeah. It's like the wordage is really makes you think.
Doctor, trying to spell physician, I always spell it. The doctor, DR, orders, you said 3, right?
Mm-hmm.
Okay. Oh, the grains, see? Yeah, I don't like the grains either.
Oh.
Codeine, I'm not gonna put the amount, every 3 hours. And then we have 15 milligram tablets. And we're looking for how many? I need to switch markers. I keep grabbing the bad one, I should just throw it away. But
A conversion figure for 1 grain is 60 milligrams.
okay, so we're starting, we need conversion factors. So 1 grain is 60 milligrams. Because we're trying to, so the reason you picked that one is because you're looking, okay, I have grains and I need milligrams. So, good. All right. I'm gonna change this fraction into a decimal because it's just easier for me. So this is what I have. And I need to figure out how many milligrams. Okay, so this is what I'm starting with, so that's what's starting my railroad tracks. That's what they gave me. I need 0.75 grains. How many milligrams is that going to be? So this conversion factor will get you there. You're multiplying, yes, exactly. 1 grain on the bottom, the 60 milligrams on top.
Mm-hmm.
Multiplying 0.75 by 60.
Yeah.
So this is, you can look at it this way, the 15 milligram tablets, if you want it in a conversion factor, 15 milligrams is